So let's talk about the 16-bit computer that I want to build. What I want to start with is the fetch, decode, execute cycle, which is sort of the core operations of the CPU. We have instructions, right? And we have two registers for instruction processing. We have the instruction pointer, and this is going to contain the next operation to be executed. So I'll put like a little lightning bolt there with an arrow. This is the next one to be executed. And then we have the instruction register, which has the actual instruction that is currently being decoded. So we have our control system here. And then we also have our RAM. And let's say the RAM is right here for convenience. So let's say this is our RAM. What needs to happen for every CPU instruction that's being executed is we need to send the instruction pointer to the memory controller, who will look up this address. So we're going to look up this address in memory, and then we're going to output the data, the instruction itself, into the instruction register. So we fetch it, and then what's going to happen is it's going to go into our decoders, like our control flow program, so to speak. And we're going to see what instruction is it, right? Is it to add something? Is it to multiply? Is it to move data? So we're going to decode what it is, and then we're going to execute. So this is called the fetch, decode, execute cycle. Now to trigger this, we need a heartbeat. And we had built an astable multivibrator before. There's a video on it if you want to see it, but this can act as our heartbeat. It just constantly pulses between 2 points. So we can use either when this LED lights up or when this LED lights up, they're opposites. We can use this as the clock pulse. But what we need to do is keep track of the state of the CPU. So we know that we have fetch, we know that we have decode, and we know that we have execute. And what I'm thinking of doing, we can use flip-flops tied together into a shift register configuration. This is a D flip-flop, but I'm going to be using a chip. This is 1 bit of data in a D flip-flop. So what we can do is we can have 1 bit that's set. You put it in red. And the shift register just shifts everything to the right. So for the first sequence, it could be 1, 0, 0. And then it can shift right. And then it can shift right again. And then once it reaches the end, it can loop back around to the beginning. So we have 1, 0, 0, 0, 1, 0, 0, 0, 1, and it keeps on going forever. So this can keep track of what stage we're on in our fetch, decode, execute cycle, because we need to build this functionality ourselves. So we have the pulse here that will trigger these movements, right? When there's a 1 here, then it will trigger our fetch operation. When there's a 1 here, it will trigger our decode operation. And when there's a 1 here, it will trigger our execute. So this is what I'll be building here, where we can use the clock output from the astable multivibrator to cycle us through the steps of fetch, decode, and execute. So this would be a fetch step, then we decode it, and then we execute it. So let's get started building this. So luckily, one of the chips that came in this kit is a shift register. It's the 74LS164. Maybe there's more, but it's one I found so far. So that's right here, 74LS164. So I feel like if we set this up, we can make our clock pulse on the shift register, rotating that 1 throughout, which will track the state of our CPU in the fetch, decode, execute cycle. So I'm going to give that a shot. So this is going to be a new board, I guess. Here's our guy 74LS164. And the configuration, we need to pull the clear high for it to work, it seems. I know this is probably really huge on the screen. So we need clear to be pulled high, and then the clock on the rising edge is going to create a high on the first input, which is weird because A and B are both high. So there's 2 inputs. I don't understand that. I see. So if there's any lows on the inputs, it doesn't even look at the other one. So they just both have to be high. That's so strange. I've never seen that before. I mean, it's not surprising I haven't seen it before. I haven't seen anything before. So let's take a look. So we need declare to be high, which is this pin here. So VCC, 5 volts, ground, high. These need to be tied together with an input. I'll just leave it high, I guess, to test it out. And I think that's pretty much it. And then the outputs. So what's going to happen is when we put in the first data, right, then A will be whatever that data is. Let's say it's a 1. So A will be 1. The next time the clock pulses, our 1 will move down, right? That's the way that the shift register works. But what we have to do to facilitate our function is we need to output the C back into the A. So it just keeps rotating. So C would go into here, I guess. And I'll need a way to set it up in the beginning, but let's just get this working first and then we can figure out the configuration. So we put in a 1 and then it just keeps rotating. A has it first, then B, then C, then A, then B, then C. Let's give this a shot. I'm gonna flip this around so it's a little closer. So positive is close and this one's close, so I can use the smallest connections possible. Okay, so here's power. We need to pull up the clear pin, which is this one. Okay, our clock goes in here and our data needs to be jumped together. And then we should take the output, I guess, of A, which can be, I guess, just like a 1K resistor. And then we can plug in our LED, ground it. And I think that should be it. we need a clock, right? So the clock of our astable multivibrator. So I'm going to take the output of the clock, and generally I like purple for clocks. I don't know why. So this should be in line with the collector, I think. And we can test that by just running it into this LED. I do need to ground it. So I have a black cable here. So we have the clock, and we can see it reflected here in this LED. So we do have our clock signal going into this unit here, just so we can see that it actually goes in. So I'm going to put it into the actual clock, because this is really the output. So I'll put it into the clock here. And maybe what I should do is have an LED for like a clock indicator or something. So maybe I could put that here. All right, so we're plugged in now to this astable multivibrator. We have our clock coming in. We have our chip here. So now all we have to do, well, right now this should be getting a 0 in, right? Because there's a 0 here. So I need to, I guess, pull this up, and then we'll see if we get a 1 on our output. Not seeing anything yet. We do have a clock signal coming in. Let me check the configuration again. We have the VCC coming in. We have the clear being pulled high. Our ground is working because we're connected, so we are grounded. Our clock is working, indicating that the ground is connected. The clock comes in. I don't really know. When I touch the clock, it seems to do something. Right now it's high, so if I pull this out. So strange. So we can see some of the functionality working, but it's not reflecting my consistent clock pulsing of the astable multivibrator. Let me try it with a switch. Okay, so we have our clock now. So let's see if we can get this turned off now. Okay, so that's off. So if we give the input a 1 again, then it gets it on, and now it doesn't. So it's a little finicky, and I'm assuming it's because I've heard oh, like, look at that, it's weird. Well, this is floating input right now. That's another thing. I need to pull down the inputs. So I'm gonna pull this one down, and then let's get our input back in. So right now it should stay low because it's being pulled down. But if we put the input back in, I'll use a small cable here, then it does seem to work. So A has a 1 right now, and then A has a 0. So it's working to get the input in there. However, it doesn't seem to work with the astable multivibrator. So let me plug this out again, plug back in my clock. Yeah, I don't know why the clock signal is not being registered over here. We have the light going off right now. It's very dim. Let me put it back directly with the actual clock signal, since I don't think I'm going to go back to the switch. I really want to get this to work. And then hopefully we can see the LED being illuminated a bit better. We see it's in sync right now with the clock. But again, if we plug this out, then it doesn't refresh this. Right now there's a 0 coming here, and it's pulled down. So there's a hard 0 here. But the clock does not cause the shift register to bring in the new value into this first A output, the first bit. But if I tap it, then it refreshes. So there's something wrong with the signal for sure. I think what I'm going to do real quick is use this cable instead for this input here. So I could just easily plug it out and plug it in. So I'm going to use the oscilloscope and check out the shape of the waveform that's coming from the clock to see if that's causing it. Maybe it's too slow of a curve or something. I'm going to turn off my light so you can actually see this. And I'm going to plug the positive onto this LED's probe right there coming from the clock signal. And then the other one I'll just put to ground, like right here, and then turn it on. Wow, that's a lot more square than I was expecting. I'm used to seeing it going up really slowly, but I guess that's because I've always taken the reading of the capacitor, but the actual output is a very clean wave, at least to my noobish eyes. I was expecting to see something very slow, which would be causing the problem, so now I'm completely thrown off. I was expecting to see a different problem here. Now, funny enough, I do see that the voltage is pretty low, 1.91. The max really should be 5 volts. I don't know why it would be so low. But man, that wave looks really beautiful. I like that. So we have a nice solid square wave, but maybe it's too weak to trigger the clock pulse on the shift register. Turn back on the light, plug this out. So I don't really see anything here about the clock voltage. I see clock frequency, but supply voltage, it says minimum is 4.75. So maybe that also means that the inputs need to also be 4.75. Not really sure. I don't see anything on here about voltage level for the clock. If anybody is intrigued, you can pause it and look, but I don't think I see anything here. I think I'm going to try and boost the voltage level with a transistor. So I'm going to plug up my power. I'm going to zoom in right here. And what we can do is just make a really simple inverter, because I don't really care whether it's in sync with the astable multivibrator or not. Although, you know, we really have 2 lights here. It's plugged out right now, but we have like a Q and a not Q, and I don't really care which one it lines up with. So an inverter is probably the best way I know to get a really high signal from a low signal. I know that we could just use it as a simple amplifier, but for some reason, I feel like the inverter like configuration is really solid. So going to put a 1K resistor into the collector, which will serve as our high power. And then the transistor is just going to be grounded. The emitter is going to be grounded. So the idea here is the power wants to go home, but it can't unless the base is pressed. So the base is actually going to get input from the clock. And then hopefully when the clock is not high, the current coming through this resistor will have no other choice but to go through the clock because it can't take that cheap way home. If I can connect another cable here. Okay, so our green seems to work. Well, really, this should be a high resistance path. That's what I'm forgetting. So I'm going to use a 10K here to make a high resistance path. So it only wants to go this way when the base is not pressed. So I'm going to plug this in and see if that changes anything. All right, so we should have a 1 on the output, and there is a 1. So still not updating because I plugged out the 1. I noticed that the asable multivibrator has stopped oscillating. He died, it seems. Oh, I shorted. I shorted everything by plugging this into the wrong slot. The multivibrator is acting a little strange. I feel like a lot of current is coming out of here. So maybe I need to use some resistance because ideally I'll just get a really small signal. So I'm going to, instead of plugging it straight into the output in parallel, I'm going to use a 10K and bridge it over this gap and then plug that in here and see if that makes a difference. So the multivibrator is still not doing what it was before. What is happening? This guy does not turn on anymore. So maybe the signal also wasn't straight enough because now we should be getting more voltage. I guess I should double check that. So let's plug this in again and see. Still getting only 1.75 volts there. How is that possible? Maybe if I plug out the LED. Now it's up to 5. Oh yeah, that made a big difference. So was the LED killing me the whole time? Let's see if it's working now. Yeah, I think it's working now. So I think what I need to do is add some more outputs here. So I'm going to plug up my power. Wow, so the LED was taking the voltage. I don't know if I understand what's happening there. But so I'm going to plug out this guy now that he's done his job. Make sure these are back in. So now what I'm going to do is I'm going to take the output of B and C. I think this is a 1000 ohm resistor. So I'll just put them right next door. And then I should have another 1000 ohm resistor somewhere here. I think this is another one. And I'll put them right next door as well. And then we just need to put in some LEDs here. So here's one. It's for bit number 2, or output B, I think is what it's called in the setup. And number 3 will go right here. So we have A, B, C. So if we plug this in, then let's see what happens. So right now B is on and it goes to 3. Yeah, so this is working out very well. Right now there is a 0 on the input. So if I plug in the input high, then we should see A fill on the next clock impulse. Ooh, I don't like that. What just happened? There's definitely some double clock impulses happening. Maybe I do need to clean it up more, like the signal. Damn, thought I was in the clear. Let's see. Next impulse turns on all 3. Definitely some weird like bouncing going on, I think. The clock, the signal is not clean enough after all, it seems, because it's pulsing many times, almost instantaneously. And that's because this guy can run at, I think, megahertz, which is, of course, millions of clock pulses per second. So any kind of shaky signal is just going to launch a bunch of clock pulses faster than we can perceive. So Eric Vincent has always talked to me about Schmitt triggers. And a while ago, I did check, and I do have one here, and I think I have the data sheet. So I'm going to find that. It's the HC14, and see if we can use that to clean up our signal from the asable multivibrator. So I'll be right back. Okay, so we have a Schmitt trigger, which is supposed to clean up the signal and create a perfect square wave. And they look kind of like hex inverters because there's 6 of them, just like the inverter chip. We just put in the power and the ground, and each of these inputs will give us a clean output. So I'm going to use the top one, A6, the one next to VCC, and then our output will just be the one next to that. All right, this looks like him, HC14. So I'm going to plug out power. I'm going to give my little home right here. And then pretty much right now, all we have to do is on the second pin, we're going to have the output of our amplifier. Although I don't need to know if we need the amplifier anymore, but I'll just keep using it. And then the output will be this one, which will be our new clock. So that just means the output of this little inverter / amplifier that we have will go right into pin 2. just like that. And then the output should be able to go straight over there. So there's our clock, and I'll just plug this guy in, and let's see if this cleans up our system. So let us plug in power and see what happens. All three turned on. I don't really like how that looks, but all right, let's see if A gets a 0. No. Man, still just turning them all on at once. What is happening? Or all off at once. That's a good sign. That's a good sign. That's a good sign. And if I plug it out, that's a good sign. That's a good sign. That's a good sign. Okay, so that seems to work. Oh, but they all turn on. Why? Why did you all just turn on? What is happening? They all just turned off instead of going one at a time. Maybe there's a wire that's like kind of loose over here and creating that kind of super rapid situation. Let's see what happens. Yeah, this seems to be working pretty well right here. I had that resistor, so this seems to be a way better. Yeah, no mistakes so far. So we're just feeding the first bit when I plug this in, and the rest will just shift down. So we should have 0, 1, 1 there, and then 0, 0, 1, and then we'll have 1, 0, 0. Okay, I plugged it in. 0, 1, 0. 0, 0, 1 should be next. Okay, this is perfect. So now what we have to do is put the output of C back into the input of A. All right, so that seemed to work, just connecting them together. Now, I do need to manually set the first one to a 1, but in the future we can make some contraption that does that. So right now it's fetch, decode, execute, fetch, decode, execute. So pretty slow, but this is essentially what I wanted. I do think the multi-vibrator signal is very unreliable, even with this trigger, but maybe I didn't configure it properly. So we sort of have data retention on what the CPU is doing in a cycle. And all we have to do now is allow each of these lights to power up an operation of the CPU. So 1 is we fetch, 2nd is we decode, 3rd is we execute, and then it keeps on looping. So let's see what's next, but it's a good start to our little CPU project. I'm excited to continue and hopefully get to the stage where we can actually do some interesting things with our manually built computer.